Okay, let's talk about recommendations now. In this book, you've been learning all about predictive analytics, machine learning, how to make predictions from a set of features. Recommendations are based on similar principles, but done a bit differently. So let's dig right into it. There are a couple of main types of recommendation. We call it collaborative filtering and content filtering. Collaborative filtering, I'm going to explain in detail a little bit more next. It involves using, as you can see here, preferences about the customer. In other words, past transactions about shopping cart, or we used to call it market basket analysis. We'd take a look at the things people purchased, what things went together in a shopping basket or market basket, and we're able to use that to recommend other items. This is actually the same concept used by Facebook and LinkedIn to recommend friends and network contacts and things like that. This is different from content-based filtering, which is when we analyze the actual product or service level features, as well as features about the user, to make predictions about their preferences. So this is more similar to what you've been doing in the past in this book. So let's dig into a very basic example here. This collaborative filtering process is based on naive Bayes or probability based outcomes. I'm going to walk you through a simple example here in Excel. Let's say that we have a store that sells 4 things: root beer, diapers, Oreos, and bananas. 4 necessities of life. We're going to represent these as A, B, C, and D here in our example. So N is going to represent the total number of products. R is going to represent the combination size. The first thing we need to do is determine the total number of possible combinations of products. So the formula for that is the combination formula, but we sum that for n minus 1 total products because for example here, we've got 4 products. N is 4, R is our combination size. We're going to do this for a size of 3. If it's a size of 4, there's just one combination and there's no need to recommend. But if there's only 3 items in a basket, well, then the total number of possible combinations is going to be 4 factorial over 3 factorial times n minus r factorial, which, as you can see, if you don't want to walk through the math in detail, you can take a look here at 4 factorial is 4 times 3 times 2 times 1. That gives us 24. 3 factorial times this, that's 3 factorial, which is 6, times 4 minus 3 is 1 factorial, which is 1. So it's 24 over 6, which is 4 plus 6 plus 4. Basically, we have 14 total possible combinations. So you can see that here, represented as I could come to the store and buy just product A, root beer, just diapers, just Oreos, just bananas, or I could buy root beer and diapers. I could buy root beer and Oreos, root beer and bananas. I could buy diapers and Oreos, diapers and bananas, or Oreos and bananas. So I've got every combination of size when R equals 1. When R equals 2, I get 6 possible combinations. And when R equals 1, I get 4 possible combinations. So I've got my list of actual product combinations. The next step is to calculate 3 different formulas, that we'll use along the way. Let me scroll down here a bit more smoothly. The first formula is support. Support is a combination of product A and B over total number of receipts. So what we're going to do is we're going to grab all of the actual transaction data for anyone who's bought products at our store, and we want to see what percent of the time does a particular combination, for example, AB here is root beer and diapers. What percent of the time does root beer and diapers appear as a percent of all shopping carts? A plus B divided by total. Now this is regardless of anything else that might be in their cart at the time, but I'm going to go through every receipt or every shopping cart and find out the number of times root beer and diapers are bought together divided by total number of receipts. I use support then, or I calculate a similar score called confidence next. Confidence is that same combination normalized by the first product. So if I want to recommend B based on A, I need to find out what percent of all shopping carts include, or what percent of A purchases include B. So whenever people buy A, how often is B included as well? So this is the total number of times A is purchased. So in our example, this is root beer. And then I'm going to calculate the percent of times that diapers, B, appears with root beer. That score is called a confidence score. I then use confidence in one more formula called lift. It's not actually that complicated. Lift is simply confidence divided by B over total. So let's explain this conceptually here. This is what percent of the time does B, diapers, appear with A, root beer, compared with all other possible products that might appear with A. So now, rather than normalizing B by the total number of times A is purchased, I'm normalizing that confidence, that score right there, based on the total number of times B, the percent of the time that B appears across any purchase. So in other words, recommending B for someone who has A in their shopping cart needs to be reduced or normalized based on the total number of times B occurs. If people don't buy B very often, it doesn't matter that B is always included with A because it's just not purchased that much. It's not going to make a big difference if nobody buys B, knowing that B goes with A often. So each one of these is a step towards normalizing or comparing a particular product recommendation to all other possible products you could recommend to make the most money. Or maybe a better way to put it is to get the highest likelihood that somebody will transact or accept the recommendation, whatever that might be. So those are our formulas. Now let's go through an actual example here. So I'm going to scroll out just a bit. Sorry if this makes it tough to see on your screen. You might pause the video so that it can download a high resolution version if you're having any trouble seeing this. But let me walk you through what we have right here. So ignore anything except for what I'm pointing to in the moment. Let's start right here. So here are my receipts, my past purchases. I can go to my transaction database, my transaction processing system, operational database, whatever you want to call it, and I can pull up all of my purchases. So let's keep it simple, and let's say we have a total of 10 purchases in our store. The first one included root beer and diapers. Now notice I'm not worrying about quantity purchased on either one of these right now. I'm just simply looking at, did root beer and diapers appear on a transaction? Now this is just one of the most simplest ways to implement collaborative filtering. There are absolutely ways to weight these by quantities and lots of other ways. But anyway, for now we'll keep it simple. Receipt 2 then has root beer, Oreos, and diapers. And let's assume this is an online store for whatever reason. And so this is the order the products were also added to the shopping cart. And anyway, and you can see so forth here, all the different transactions included. My next step is to then, based on the number of products I have, determine the total number of product combinations. Now we did that previously already, remember? That's our formula right here up at the top. We determined there's 14 possible product combinations. We spell them out right here, A, B, C, D, A, B, A, D, A, C, A, D, and so forth. Then I'm going to go through and count the total number of times that each one of these product combinations appears in the actual data set. So let me spread this out a bit. I'm going to keep things looking nice here. There we go. A little bit OCD here as far as things looking perfect. There we go, that's better. So my count, root beer alone, I'm just going to go through. This formula is a simple count if, a count if equals root beer. So total number of times root beer appears, 7 times. And for these first 4, it's the same thing for each of them. I'm simply counting the number of times that that product appears. Over here, I have the total number of actual transactions, 10. So support is just a simple number of times this product appears divided by total. That's my combination, or my A plus B divided by total. Now in this case, it's just A. There is no B because it's a single product. Pretty straightforward. But here we have AB combinations. So Oreos and root beer, how many times does that appear together? Not here. Here it does. It doesn't matter which order it's in. It's agnostic, but I've got 1 right there. Not there, not there, not there, not there, not there, all the way down to here. Here's my second. Oreos and root beer. So I have 2 of those. I think I just hard-coded that in, yeah. I'm sure you could come up with an Excel formula if you wanted to make that work. But I went through and just counted up the number of times each of these combinations appear. Now I'm down to my A plus B plus C combinations. So Oreos, root beer, and bananas. Some of these, as you can see, don't appear anywhere. I've put in all possible product combinations, but you can, as you might guess, you can speed up transactions or speed up model training for recommender systems by not calculating support for combinations that don't exist in the data set. But we're not going to worry about that for now. All right, so I've got my combinations table and my support calculated. Now skip this table and I want to go over here. What we do next is create a series of rules. These are the rules that we're trying to come up with a confidence and lift score for to determine how likely or what I should recommend. For example, if I have Oreos in my cart, then what is the confidence and lift that I'll add any of the other products? Now, if you have a big database like Amazon with millions of products, literally, then this is going to get pretty big. And you're going to have to find ways to either get a lot of processing power or keep training small, or maybe train on only subsets of the data, which is probably what they do. I'm sure it's what they do. So what we have here is confidence. Let me show you how that's calculated. This is the formula that we referred to back here on, oops, not that one, on this page right here. So this is A plus B divided by A. Let me show you how I implemented this in Excel here. I'm going to get off of that right there, and I've got a hidden column right here, R. Unhide that and show you what I'm doing. So to get confidence, get A plus B over A, I'm going to treat Oreos as A, root beer as B, and I'm going to divide by the count of A. So it's the count of A plus B over the count of A. Now the way I do that, since I've got it listed here, product combinations, they're separated by commas. The easiest way I found was to grab every combination and put it here in column R so that Excel I could use a VLOOKUP on this value right here to return that to confidence. So right here, this is going to refer to that one because I've got my Oreos and root beer. All right, I'm going to rehide that again so you can see what's going on now. So back to my formula. My count of A plus B, I get that by referring to that hidden cell, and it goes and looks at Oreos and root beer right here and grabs that count of 2. That's what's going in right here and being returned right there. So 2 divided by, and then it's a more straightforward VLOOKUP where I look up just Oreos in the same table and it pulls up 4. So Oreos plus root beer divided by Oreos, those counts, that gives me my confidence score right here. And I go through and do the same thing for all these. For these triples, where I've got 2 products and I'm trying to decide what the third product is to recommend, I am referring to, for Oreos, root beer, and banana, I'm referring to the count right here, Oreos, root beer, and bananas. That's 0 divided by the count of the count of Oreos and root beer, which is 2. 0 divided by 2 gives me 0. Let me show you another one. Okay, here I've got Oreos and root beer and diapers. That's this one right here. Count is also 2. Count is 2 for this one. And then I divide it by Oreos and root beer, which is 2. So 2 divided by 2 is what gives me my 1 right there. So that's my confidence score. It's the percent of time that this column right here in the then space is appearing with this column over here. Now look at this example, that's a 2. Let me see if I've done something wrong possibly. So here I've got the number of times that Oreos, diapers, and root beer appears. Where's that one? Oreos, diapers, and root beer, 2, divided by the number of times that Oreos and diapers appear, which is right there, 1. So that's what gives me a 2. So it's not technically a percent score. I guess you could say 200% of the time. Anyway, my point is that confidence doesn't just range from 0 to 1. It can be higher than 1. Okay, then lift, finally, as a reminder, it's confidence divided by the percent of time that this product here, B, in the then side, appears in all transactions. So basically the count, actually it's the support for B, because B divided by total, I just go and grab the support for whatever product here that I'm referring to. So let's give you an example. Here are my Oreos and root beer. This score is going to be, it's going to look up the confidence for Oreos and root beer, which is right here. I've already got it calculated. I divide that confidence by the support for the root beer. So that's what I've got my VLOOKUP table for right here. This says go over here and grab column 4, or the support column for the row that equals root beer, which is this one. So this is giving me 0.5 divided by 0.7. That's how I come up with 0.714. So lift represents then a normalized comparable score representing the likelihood that somebody will want that product if they have this product already in their cart. So if I have Oreos in my cart and nothing else, which product do I recommend? I recommend the alternative product with the highest lift score, which in this case is bananas. So, and then after that, then it's going to be root beer, then diapers. So what I've done here is I've created this recommendation table where I go through each one of these combinations, and it's irrelevant for these combinations of 3 because in each of these cases, there's only one product left to recommend. So there's no point in coming up with the recommendation for those. But for these where there's only one product or 2 products, this is very relevant. So if someone has root beer in their cart, I recommend first that you offer them diapers, then bananas, and third is bananas. Well, how does that happen? Let me show you. So over here, let's go to where root beer is. It's this one. I look at root beer and say, okay, if they have root beer in their cart, then the lift for diapers is our max score. So that's why that one's number 1. And now you can see that bananas and Oreos have the exact same lift score. And so my formula that said grab the second highest value, it treats bananas as both the second highest and the third highest. It's just the way Excel works. Let's go to a different example here. Diapers. I've got diapers in my cart. Now this makes sense then that the first recommendation is root beer, because if I have root beer in my cart, the highest recommendation is diapers. Although that's not always the case. But anyway, diapers, let's go to that one right here. If they have diapers in their cart, the highest lift score is for root beer, second highest is for bananas, third highest is for Oreos. That's what I've got right here. So if I'm a grocery store manager, what can I do with this? Well, this tells me what products I want to put next to each other on the shelves. If I have root beer here, then I better put diapers next to it, and then maybe bananas next to that. This is the exact type of analysis that is used to design and lay out grocery stores. Not just grocery stores, but all types of retail outlets when they're determining what products to put next to each other. And if it's not used, well, then they're idiots. It's such a simple formula, and any mall store could do this and use it to put products next to each other that are going to be more likely to increase their sales because they're physically easier to get to or see. Same thing if this is an online store. Clicks cost money. The more you make someone click to get to what they want, the less likely they are to get it and make the purchase. So if this is not currently being done on a website, then that website's losing money. Anyway, let's check ourselves now and see just how accurate our recommendations are. To do that, scroll over here to the left. Well, I guess I'll scroll and you'll watch. And let me show you how we check. Okay, let's go through each one of our receipts and see how our recommender would have done with what those people actually wanted with their orders or with their shopping carts. So this person started out and put root beer in their cart. Now, if someone just had root beer in their cart, what would we be recommending? Well, we come over here, we find the root beer product recommendation, and we can see the first recommendation on that list is diapers. Perfect. Okay, if I keep scrolling over here, you can see, I've hidden them. Let me show you. I went through and I scored this with an accuracy metric. So if the product they got second is the first one on our list, I'm going to give it a 3. If the one that they got second is the second one on our list, I'll give them a 2 and then a 1. And so what we've got right here is I gave this receipt, I gave this receipt a 3 because we recommended diapers as the first option if they had root beer in their cart, and that's indeed what they had second. All right, so this one, they got root beer, and then so we know that the recommendation is diapers, but their second product was Oreos. So come over here, and if they have root beer, Oreos doesn't show up on the list at all. So for this one, the second product was wrong. If indeed I'm making the assumption that they added products one at a time in this order. That may not be the case if it's an actual grocery store. You wouldn't be able to tell that. But I'm going to assume that this is maybe an online website and that I was able to record that for argument's sake. All right, so now they've got 2 items in their cart, though. With this combination, what do we recommend as their third item? So we come over and find the root beer Oreos combination, which is right here. If they have root beer and Oreos together, it doesn't matter that these are in the reversed order right here in this combination. But if they have those 2 together, our first recommendation is diapers and then bananas. Now, we don't have a third one because we only offer 4 products and they've already got 2 in their cart, so there are only 2 recommendations we can make after that. But what did they get? Oreos and root beer. Sure enough, they got diapers. And that was our first recommendation over here, so I gave this one a 3. Actually, you know what? I should probably give it a 2 since there's only 2 possible. It doesn't matter. We'll leave it as a 3. Okay, next. They had Oreos. We recommended bananas. Or they have Oreos. Let's see what we would have recommended. Yep, Oreos. First recommendation is bananas. Sure enough, that's what they got second. Okay, we were right on that one. Got a 3. Root beer. We already know from experience that if they have root beer, we recommend diapers. And sure enough, that's what they got. So they got a 3. We already have an Oreos bananas from up here. So that one's got a 3. Right here, root beer, we recommend, that means we'd recommend diapers. Sure enough, they have diapers. But what if they have root beer and diapers together? We come down here to the root beer and diapers together and find out that the first recommendation is Oreos and then bananas. All right, well, the second one was right, so we only got 2 points on that one. Yeah, it's kind of artificially inflated, isn't it? Let me change this one to 2 and this one down to 1. Okay, root beer diapers, we know that that one is correct. Diapers, bananas. Okay, if they have diapers, we know the recommendation is root beer, but they actually got bananas, which was our second item on the list, so they've only got a 2. Right here, diapers, root beer, we know that's correct. Diapers, Oreos. Okay, if they have diapers in their basket or their cart, Oreos is the third recommendation, so they only got 1 point for that one. Actually, you know what I'm realizing? Well, hold on, let's finish this example out first. Diapers, Oreos together, right here, diapers and Oreos. We recommend root beer next, and sure enough, that's what they got. So they get 3 for that. So up here, I put 0 points, and I'm realizing that's because when they had root beer, let's see, the next thing they got was, right here, root beer. We recommended diapers, bananas. That's only, one of those should have been Oreos. And since bananas and Oreos had the same lift, we shouldn't give them 0 points. We should be giving them like, it's the average between 2 and a 1. We'll give them a 1.5. I think that's a bit more fair because Oreos should have been one of those in that list. It was just that Excel bug that didn't show it to us. Whoops, that's too much. Okay. So we've got our score. What I want to do is simply add this up and divide it by the total possible score. Total possible score is going to be 3 times, what is that, 10? So 30. This one, the highest is a 2, 32. 30, the highest possible there would have been 2, so it's 34. This should actually be a 2. Because they had diapers and Oreos, we recommended root beer. For diapers, Oreos, they got root beer, so that's a 2. Okay, so total is 36 possible. And we summed up all of those divided by, this is off a little bit too, count times 3. It's actually the count of just A4, whoops, didn't mean to do that. Count of A4 to A13 times 3. Plus the count of B4 to B13 times 2, because 2 is possible on that second one. And I'm going to put, I better put parentheses around this one and right there. There we go. All right. 84% accuracy score. That's not bad at all. So our recommendations were correct. Weighted, because we have a ranking rated here, based on our weighted ranking, we were right 84% of the time. So that's how a basic recommender works. Now the way Azure works is going to be based on this concept, but a bit different. So the way Azure works, it actually wants you to know, it uses what's called a user item rating triple. So it wants to know who the user is. Let me go back to an example here, not Shutterstock, this one. Let's skip ahead to this chapter, or this section. The format it wants the data in is right here. It wants a single row to have a user ID, and that can be either an actual primary key ID or a name or something that uniquely identifies each user. Then an item ID, and then a rating or some indication of how much they like that. So because online we're typically dealing with ratings and not necessarily just the presence of something being in a cart. Well, no, we are actually. We're doing that too. But the way Microsoft decided to implement this tool, they use this user item rating triple. So in the context we were just using, a rating could be construed as like a quantity purchased. So Homer football, maybe quantity purchase of football, and then I get a record for each product that Homer's purchased, maybe a quantity purchased. The only problem with that then is you only get the products that Homer's purchased. The ones he hasn't purchased, we assume he doesn't like those. Sometimes you have to enter additional records in Azure with a 0 for the quantity to indicate that this person didn't buy those other products. But we'll come back to that later. For now, just know that Azure wants a user item rating triple, and rating has to vary between, there is a limit. I think it's got to be a whole number between something like 0 and 100. I could be off. It might be 0 and 20, 0 and 50. I'd have to take a look. But it assumes this rating is not going to vary between like negative infinity and infinity. It's going to be a whole number in a given range, I think up to 100. So how does that play out here in our example? Well, over here on this page, I copied that example, and I'm going to turn off grid lines to make this a bit easier to see. All right, what if in our initial receipts table, we knew who made each purchase? So in this case, it's not just a receipt, but it is a receipt with a customer ID. This better represents today's market because every grocery store wants us to use a membership card, right? Or you go to the mall and buy some jeans and they say, what's your email address or what's your phone number? They want something to tie together purchases. So that way they know that, okay, this receipt was Homer, but this one is Homer as well. So it's not just root beer and diapers that goes together. It's actually root beers, diapers, and Oreos that go together for this particular customer. That's better data. Now, grocery stores have been doing this for a long time without you knowing. Anytime you pay with a credit card, most of them have been storing your credit card number. And then every time you pay at that grocery store with a credit card, they know that it's the same person again. And they're able to tie those things together. Very sneaky, right? But they like it even better if you'll use some membership card, because what if you have 2 different credit cards or several credit cards use that store? They want to be able to tie together as many of your purchases as they can. Because if they do that, they get even more accurate predictions. So let me show you how this plays out. So now our table shifts, and I've changed the structure here to where it looks more like that format that Azure wants it in. Where I say, okay, I've got a user item rating. In this case, rating is going to be a quantity. But what I had to do is go through and create entry for every possible product we sell for each customer. So in this case, the rating for root beer is 2, the number of times Homer's purchased it. Diapers, 2, Oreos, and then bananas. He's never purchased bananas, so they get a quantity of 0. And that concept of rating inferred in the Azure context, it assumes that if they're rating 0, they don't like that product. So if they haven't purchased it, it's because they don't like it. So theoretically, that makes sense and that works. But I've got to go through and create a record for every customer, every item, if this is the way I want to implement it in that Azure tool. Now, if you have a ton of items, this might not be realistic. Or maybe you'll have to grab a random sample of products that they haven't purchased and generate records for those with a quantity of 0. But instead of doing it for every product, you can use a random subsample to try to minimize your data set so it doesn't take so long to train. And you'll see when we get into Azure that it does take a long time to train these recommender models if you have a lot of data. But anyway, here's what else has changed. Now that I have my data tied to customer instead of receipts, how do I calculate support, confidence, and lift? Well, it's just a little bit different. Now, my count of each product is the number of customers who have purchased it, not the number of receipts it appears on. So I have 5 total customers, and it appears on 4, it's been purchased by 4 of those 5 customers. Now my total possible customers, right here I have the 785 because I was trying to use a weighting system. There are only 5 total customers. However, I use this weighting system to indicate the number of times that each customer has purchased it as well. But I think to keep my example simple, I'm not going to get any more advanced than just using a total number of possible customers here. So I go through that and do it for all product combinations just like I did before. My total now changes based on the number of customers rather than the number of receipts. I calculate support just like I did before, and all my formulas just go ahead and propagate. So here, lift is a bit different. All of these and confidence is a bit different because of the way I'm coming up with my count and my total. The real question now, though, is this any more accurate than the other model? Well, let's find out. I'm going to hide these temporarily, and I'm going to insert some places to keep track of the score. So let's keep track here of second product and third product. Oh my gosh. There we go. Okay, so I hid a little bit too much. I need to still be able to see my user item rating triple right there. Okay, perfect. So Homer, he has now this is a bit different. I'm not counting the number of things he puts in his cart. Let's simply go through each item that he's purchased and see what the next recommended item is. So Homer has root beer. If he has root beer, we recommend diapers. So the way I would probably score this, I'm going to sort first by, and this is just one possible way to do this. There's many ways to go through and score accuracy here, but I'm going to sort this by customer first and then by quantity next. Sorry, I need to add another level. Quantity next. Largest to smallest. Okay, there we go. So Bart, his primary product is Oreos. What should his secondary product be? That's how I'm going to score the accuracy. So here, Oreos, if someone has Oreos, the next most common product should be root beer. And he actually has 0 root beer. So his second product, now these are tied. So let's look at bananas. If he has bananas, the recommendation then is also root beer. So since these are tied, both of them, root beer is much later on the, if he has Oreos right here, bananas are second and third on the list. So I'm going to give him a 1.5 for that. And then since it's tied with bananas, all right, so let's say he has bananas right here. The recommended is root beer, but his next highest, assuming bananas is the highest, would be Oreos, which is our third one over here. So in this case, I'm going to give him a 1 for third product. And then he has 0 of the other two. So and we might need a fourth product. So this isn't product. I would call this actually first recommendation, second recommendation. Okay. So let's go for Homer. He has root beer. That means he should be buying diapers after that. Perfect. That's exactly what he does. Diapers is number 1. So I'm going to give Homer from root beer to diapers. I'm going to give him a 3 for that. And then going from diapers, the next highest product should be root beer, which it is. So I'm going to give him a 3 for that. And if he has, and here I just need my third recommendation spot. So for Homer, where he's got 3 products purchased, if he has root beer and diapers, what should his third be? Root beer, diapers. It should be bananas. But instead it's Oreos. However, this is a case where bananas and Oreos were tied. So rather than, I'm going to give him the average of a 2 and a 1, so I'm going to give him a 1.5 for that one. All right, let's go to Lisa. Her highest is diapers, which means she should buy root beer next, which it's tied with bananas. But I'm going to call that good since it is second. So I'm going to give her a 3 for that one. And then her second highest, we'll say, is root beer. That means it should be diapers. Well, that is the next highest one after root beer. So I'm going to give her a 3 for that. And then if she has root beer and diapers, what should be the next one? Root beer, diapers. It should be bananas, but that's where bananas was tied with the other one, but that's okay. I'm going to give that one a 2. Well, I guess technically, to be fair, it's kind of artificially lower. No, I'll stick with the 2 to make it comparable. Okay, Maggie, root beer, diapers, diapers, root beer. That we know is going to be a 3 and a 3. If she has root beer and diapers, the third one she had was Oreos, root beer, diapers, but Oreos is tied with bananas. So you know what? I better stick with a 1.5 here because I'm going to give Maggie a 1.5 there because Oreos is technically tied with bananas. And so I don't want to, well, I could make this one 2 and that one 1. Either way, it doesn't matter. All right. Last one, Marge. Root beer diapers, 3 and 3. Her third one is bananas. She's got the same issue. That is the next recommendation right there. I'm going to give her a 1.5 as well. Okay, so here's our accuracy when we know who the customer is. So the total here, I'm going to say sum of, equals sum of all this is 32.5. And the total possible, though, is, 3 times, what do we have here? 5, 10. 3 times 10 plus the total possible for these are 2 each, so it's another 8. 3 times 10 plus 8, 38, equals this divided by that. All right, here's our accuracy score, 85.526. How does that compare? Let's turn that into a percent here. How does that compare to our accuracy score when we only knew the receipts and we didn't know the customers? Oh, take a look. We're a little bit better. 84.72 compared to 85.53. So hopefully you understand now why grocery stores in the late 90s, more like early 2000s, there was this dramatic shift for all stores. Well, it was first started with grocery stores to start adopting membership programs. And it was for this reason right here. The accuracy, when they knew who made each purchase, always goes up. With very, very rare examples otherwise. I've actually never seen one. And even in my super simple example here with totally random data, it gets better when we're able to tie together the purchases. So hopefully this makes sense. The way recommender systems work, this is very rudimentary and simple, but very accurate as well. Today's recommender systems have all sorts of methods for how to weight totals, how to weight counts, and a lot more really cool advances that we won't go into here in this beginner introduction. However, I just want to recap some stuff for you here. I'm going to hide this again. And as a reminder, high level, if this is what they have in their shopping cart, product combinations, then this is what we recommend right here, this list of recommendations. And it's based on these rules right here that are generated, if-then rules based on support, confidence, and lift. Again, lift is a comparable metric that, and when I say comparable, it means that if I have Oreos in my cart, I can then pick the highest lift score to choose which product to recommend first. And then lastly, it's generated from, so if we have this in our shopping cart, this is what we recommend based on these rules and generated from this receipt data. And that's it for Recommender. Move on into the next section and you can learn how to implement this in Azure.